Hello, in this video I'm going to be discussing Chapter 2, Section 2.4 and 2.5 from the book Basic Sentential Logic and Informal Fallacies. Section 2.5 will be talking about relations between statements, in particular the relations of equivalence, consistency, and implication. And then in Section 2.5 the topic will turn to validity. So equivalence, consistency, implication, and validity. This is going to be all of the topics I'll talk about. First, we'll just talk about relations between two statements, in particular determining whether two statements are equivalent, whether they're consistent, and whether there is an implication relation between them. We'll then move on to relations between three or more statements, the same relations, and we'll see it's just a trivial upgrade from what we did with two statements. And then finally, once we've done all of that, we'll have all of the things we need to be able to assess argument validity. So first up, relations between two statements. So in a way, just as it's often helpful to know whether an individual statement is a tautology, a contradiction, or a contingency, it's also often helpful to know what relations hold between two statements. And the relations that we're going to be interested in are as follows. So the first relation is equivalence. And two statements are equivalent if and only if they have identical truth columns. Okay, and another way you could think about that is that no matter what universe you are in, right, if you go to some parallel universe, those statements are going to have the same truth value if they're equivalent. To test for equivalence, you construct a joint truth table, and that means it's a truth table that has both of those statements on it, so you need them both on the same truth table. And then you just compare their truth columns. And the truth columns is just the column of T's and F's on the truth table underneath that statement. That's the statement's truth column. If those columns are identical, meaning that it's exactly the same pattern of T's and F's all the way down, then the statements are equivalent. If they're not identical, if there's any difference whatsoever, then they are not equivalent. That's going to be pretty easy to assess. Consistency is also going to be very easy to assess. Two statements are consistent if it's possible for them to both be true at the same time. One way to think of this is that, again, think of it in terms of possible worlds or alternate universes. There's some universe in which both of those statements are true. And to assess this, again, you do a joint truth table, and you just look for a row. It only takes one, but it could be more than one, but one is the crucial number. You look for any row on which both of the statements are true. And if there is such a row, they're consistent. If there's no row on which they're both true, then they are inconsistent. Now finally, we're going to look at implication, and this one's a little bit trickier, but not too much. One thing that's tricky about it is that equivalence and consistency are symmetrical relations, right? If statement phi is equivalent to psi, then psi is equivalent to phi, and same thing with consistency. So we can often just speak of two statements being consistent or two statements being equivalent. Implication isn't symmetric, meaning that it might be that phi implies psi, but not vice versa. So when we talk about implication relations, we have to specify a direction, so to speak. We have to ask whether phi implies psi, but it's a different question whether psi implies phi. Phi might imply psi, but not vice versa, perhaps. Okay. So that's just makes it a little bit more complicated in terms of how we state the question. So here's the definition. Statement phi implies statement psi, if and only if. If phi is true, then psi must be true. Okay? You can think about this again in terms of universes. Any universe where phi is true is going to also be a universe where psi is true. Or alternately, any universe where psi is false will be one where phi is also false. Now to test for this, Also going to do a joint truth table. The test is going to be a little bit more complicated, but not too much. You do a joint truth table, and you look for what we're going to call a counterexample row. Okay, right here, counterexample row. This is going to be a row where phi is true, but psi is false. So on that same row, you get that pattern of trues and falses. Phi is true, but psi is false on that row. That's called a counterexample row. If there is a counterexample row, then the implication does not hold. Phi does not imply psi. Okay? If there's not a counterexample row, then the implication does hold. Phi does imply psi. Now this will make more sense once we see a few examples. So here's the sort of thing that will show up on the test. I'll give you two statements. Not P and Q, and then the next statement is not P and not Q. By the way, students often early on ask the question if these two things are the same, or when they will translate from English into our formal notation and you get a translation like this, they'll ask if they can just instead write it as that. In effect, they're asking if you can distribute the tilde. And I say no, but I don't really explain why. But now we will be able to see why. We can ask if these things are equivalent or not. And in fact, that's going to be one of the questions that we'll be able to assess now. So the first thing you need to do if you're going to assess equivalence, consistency, and implication questions is to do a joint truth table. So this is what the truth table will look like. And if you'll notice, the last two columns are statement 1 and statement 2 in order. By the way, when I construct these truth tables, I try to sort of do it to make my life a little easier. Now I could have done, put not P and not Q. I could have done it in column 5 here. I could have done it in column 6. But I arranged it such that I had my statements 1 and 2 at the end in order. Now it's not always possible to do that, but if you can, it just makes your life a little easier because now I'm just assessing these two columns that are right next to each other. Okay, so there's my columns, or my joint truth table. Now I'm going to ask some questions. Are statements 1 and 2 equivalent? Well, to assess that, we just have to see if their truth columns are identical. We just go down row by row and see if they have the same truth value in every row all the way down. And we can see they don't, right? So over here in row 2, they have different truth values. Now, it only takes one row. They also have different truth values in row 3, but it doesn't matter. As soon as you find any difference, you know they're not equivalent. So the answer is no. Are they consistent? Well, now we're just going to look for any row where they're both true. And if you look down, you can see that sure enough, in row 4, they're both true at the same time. So yes, they are consistent. It only takes one row. Okay, now let's ask about implication. Now, like I said, it's asymmetric, this relation. It's not symmetrical. So we can actually ask the question in two ways. We can ask if 1 implies 2, and we can ask if 2 implies 1. And we might get different answers. So first, let's ask if 1 implies 2. Okay, now recall, the first thing we're going to do is look for a counterexample row. And since we're asking if 1 implies 2, the counterexample row will be a row where 1 is true, but 2 is false. So we're going to look for any row where this statement is true, but this statement is false in that same row. Okay? And sure enough, you can see that there is such a row. Row 2 has that pattern. Statement 1 is true, but statement 2 is false on row 2. Now there's also a counterexample row on row 3. But that doesn't matter. As soon as you find one counterexample row, you can stop looking for counterexample rows because you only need one. So step 2 is, if you do find a counterexample row, which we did, the implication does not hold. Okay, so that's where we're at. So the answer then is no, 1 does not imply 2. We found the counterexample row, so the implication doesn't hold. 1 does not imply 2. Now we can ask a different question. We can now ask, does 2 imply 1? So now we're going to look for a counterexample row where 2 is true, but 1 is false. Okay, so that's going to be the counterexample row we're looking for now to answer this question. Okay, here's statement 2, here's statement 1. We're going to look for a row where this is true, it's true here, but it's false in this row here. Okay? Now remember, if we do find such a row, the implication does not hold. Okay? But if we don't find that, then it does. And you can see there isn't any such row. There's no row where we have a T here and an F there. Okay? So there's no counterexample row. So the implication does hold. 2 does imply 1. Okay. By the way, I just want to reiterate again, the first thing we showed here is that these are not equivalent. So if when you were doing translations, you thought that if you translated something like this, you could just rewrite it as that and it would be the same thing. Now we can see it's not the same thing. And also, if you think it through carefully what these two things mean, you can also sort of see intuitively that they're not the same, but I'm not going to talk about that now. What I am going to talk about is the next example. Two statements here, A if and only if B, and if A then B, and if B then A. First step, do a joint truth table, and it's going to look like this. Again, I managed to arrange it so that I have my two statements in the last two columns in order. Let's ask our questions. Are 1 and 2 equivalent? Well, do they have the same pattern of T's and F's all the way down? Yeah, in fact they do. True, false, false, true, and true, false, false, true. They're both exactly the same. So yes, they are equivalent. Next question. Are 1 and 2 consistent? So now we're just looking for any row where they're both true. And sure enough, row 1, they're both true. So they are consistent. And again, yes, they are also both true on row 4, but that doesn't matter. As soon as you find one row where they're both true, then you can just answer yes to the consistency question. It only takes one. Does 1 imply 2? Okay, so remember, we're now asking if 1 implies 2. So we're going to look for a counterexample row. That's going to be a row where 1 is true, but 2 over here is false. Okay, and you should be able to see there's no counterexample row. There's no row where we have a T here and an F there in the same row. So no counterexample row means the implication does hold. Now let's ask if 2 implies 1. Now we're going to be looking for a counterexample row where 2 is true, but 1 is false. Okay, can we find a row like that? Again, no, there's no row where we have a T here and an F there. So no counterexample row means that the implication does hold. Okay, let's do yet another example. Here comes the joint truth table. Now, again, I managed to put the statements in the order I want. I want to talk about that a minute now because sometimes students just have questions about what order do you have to do the columns for statements in, and when can you get them in the order you want them in, and when can't you get them in that order. And we'll see some examples later where it's not possible to get the statements you're going to be comparing at the end of your truth table in the correct order for reasons that I'll explain right now. So before I start answering the questions, let me show you another way that I might have done the same truth table. So notice here I've got not M at the end, but you could have also done the truth table this way. I could have done not M here in column 3. And in fact, usually I would do the negated atomic statements right after the atomic statements. Okay. So why do you have variability sometimes and not others? Well, here's the key thing. You can't do a statements column. Okay, so for instance, I can't do the column for this statement here unless I already have the columns for that statement's components. Okay, and here I do, right? The components of this statement are this conditional and that negation, and I've already done those. The conditional is here, and the negation, not n, is here. Okay, so I'm good. I'm doing this statement after I've done the components of that statement. Okay, which means I couldn't do something like this. I couldn't say, okay, I've got m, n, not m, not n. I'll just do statement 1 here, and then, then I'll do this conditional, if m, then n. Okay, I can't do that. Why? Well, you can see why. Because when I start trying to fill out this truth column, I want to say, okay, this is a conjunction. It's going to be true when both conjuncts are true. Are they both true in row 1? Well, the second one is false. The first one, I don't know. I don't know if it's true or false here. So you see, I can't do this column now because I need to know what the values are of this statement before I can do the values for this statement. Okay. So that's just to say that, sort of explain why you can't do a column for a statement unless you've already done the components. Okay. So, but now if we go back to the way that I did the truth table, that I'm going to do it for this, notice I've satisfied that rule. I'm doing the atomic statements. Now at this point, I could do this conditional because both the components are just the atomic statements. So I could do that if I want. I could do this next in column 3 because its component is n, which is an atomic statement. I could do not m next. So any of these 3 I could do immediately after the atomic statements because I have those components. I could also hold off on this one until the end. Why? Because not m, this negation, isn't a component of any of these others. Okay? So I don't need not m to construct the truth table for that, the truth column for this, or this, or this, which means I can hold off till the end. If not m played a role, let's say in this, suppose this was not, if not m then n, then I wouldn't be able to do that. I'd have to do this before I could get this column going. Okay, so that's just some explanation for what you can and can't do in terms of the flexibility with when you do columns. Let's go ahead and, now that we've got our joint truth table up, let's address our questions. Are statements 1 and 2 equivalent? And again, we're looking at the last 2 columns. Okay. Column 5 is statement 1, and statement 2 is the last column, column 6. Are they equivalent? No. If you look at row 3, you can see that they're different. 1 is false, but 2 is true. So they're not equivalent. Are they consistent? So now we're just looking for any row where they're both true. And sure enough, row 4, they're both true. So yes, they are consistent. Does 1 imply 2? Okay, so now we're going to be looking for a counterexample row where 1 is true but 2 is false. So we have a true here and a false there. That'll be our counterexample row. And you can see there's no row like that. There's no counterexample row. So if there's no counterexample row, that implication holds. 1 does imply 2. Now let's ask, does 2 imply 1? Now we're looking for any row where 2 is true, but 1 is false. And sure enough, row 3, 2 is true and 1 is false. So we do have a counterexample row for that. So if there is a counterexample row, the implication does not hold. So 2 does not imply 1. Okay. Let's move on now to talk about relations between 3 or more statements. That's going to be very similar because it's the same relations, equivalence, consistency, and implication, and they're assessed in more or less the same way. Okay, so it's not going to be a whole lot more complicated here. So let's start off with equivalence. A set of statements set of statements is equivalent, are equivalent, if they all have identical truth columns. It should be if and only if with two ifs. Consistency. A set of statements are consistent if there's at least one row on which they are all true. Okay, so that's pretty trivial increase in difficulty from assessing two statements. To assess 3 or 4, you just, are they all identical? And if they're all identical, they're equivalent. And if there's any row in which they're all true, then they're consistent. So it's just like assessing 2. Implication is a little bit more complicated. Why? Well, first off, we're going to call it joint implication. And remember that implication is an asymmetric relationship. We have, in the case of 2, we could either have statement 1 implying statement 2 or 2 implying 1. When we get to a larger set of statements, then the question is, well, what does it mean for it to be asymmetric, right? Well, here's what it means. We're going to assess implication with a set in the following way. We're going to split the set into two parts. There's going to be the impliers, right? In this case, I'm just calling them phi 1 through phi n. So suppose my set of statements is 5 statements. Then n will be 4. I'll have phi 1, phi 2, phi 3, phi 4. So all of them but 1. And I can ask, does that set jointly imply the other one, psi? Okay. And this will make more sense when we see some examples. And the definition is, if phi 1 through phi n are all true, right, these 4 statements say, then psi must be true. Now to test that, we're going to test it in essentially the same way we did with 2 statements. We're still going to look for a counterexample row. It's still the case that if we find the counterexample row, the implication doesn't hold, and vice versa. So that's all the same. The only thing that's slightly different is, what does the counterexample row look like? And specifically, here's the definition. The counterexample row is going to be a row in which all of these statements are true, phi 1 through phi n. They're all true, but psi is false. Okay, that's what the counterexample row is going to be. So that'll make more sense when we see some examples. So here's a set of 3 statements. Let's do our joint truth table. Again, I'm good. I managed to get the statements in order at the end. I'm going to go ahead and just put numbers up there to indicate that. And let's go through our questions. So our 1 through 3, is that set of statements, is it equivalent? Are they equivalent? Well, they're the same. Sure enough, they have exactly the same pattern of T's and F's all the way down. So they're equivalent. Now that's kind of interesting. If you stop and look at that, these 3 statements, if G then H, if not H then not G, and then either not G or H, we just showed those are all equivalent. Now you might not have thought that they are because they look different, and if you express them in English, they're going to sound different. But logically, they're actually equivalent. They're all saying the same thing. Okay, let's move on. Are they consistent? Well, now we're just looking for any row where they're all true. And sure enough, row 4, they're all true. Also on 1 and 3, but as soon as you spot one row where they're all true, you can stop looking. So yes, they are consistent. Now let's ask some implication questions. And here's the way the implication questions are going to look. We can ask, do 1 and 2 jointly imply 3? Okay, so now we're going to look for a counterexample row where 1 and 2 are true, but 3 is false. So where 1 and 2 are true, but 3 is false. Okay, is there any such row where we've got 1 and 2 are true, but that we have a false here? No. So there's no counterexample row, so the implication does hold. Yes. Okay? And it would be the same thing if I asked, do 2 and 3 jointly imply 1? We'd look for a counterexample row where 2 and 3 are true, but 1 is false. Okay? Before we move on, I want to ask a couple questions here. Question number 1 that I want to ask. If you have 2 or more statements that are equivalent, are they necessarily consistent? So suppose I give you some statements. It could be 2, it could be 5, it doesn't matter. And you do the joint truth table and you find out that they're equivalent. Okay. Does that knowledge, can you then immediately answer the consistency question without having to look at the truth table again? Okay. Answer, no, not necessarily. Why? If the two statements are contradictions, then they'll be equivalent, but they won't be consistent. So for example, this isn't a real truth table, but suppose I had 2 statements here that I did a joint truth table for. And suppose it turns out that they're both contradictions. They have F's all the way down. Well, these 2 statements, they'll be equivalent, right? Because it's exactly the same pattern all the way down. But they won't be consistent because there's no row where they're both true. Okay? Next question. If 2 or more statements are equivalent, can you tell what the answers to the implication questions will be? If so, how? And what will the answers be? So for example, this actually came up because in the last set of statements, it turned out they were all equivalent. So the first question I asked is, are the statements 1 through 3 equivalent? And the answer was yes. The question here now is, well, once we determined that, could we have answered the implication questions without looking at the truth table again? And interestingly enough, yes, we could. Okay, we could have saved ourselves a little bit of work. Why? Well, notice that all implications are going to hold among sets of statements. Well, all implications will hold among. Oh yeah. If the statements are equivalent, then all implications will hold. Okay, so the answer is yes, we can tell what it's going to be, and the answer in fact is going to be yes. 1 and 2 will imply 3, 1 and 3 will imply 2, 2 and 3 will imply 1, and we know the answer is yes. How do we know that? Just because they're equivalent? Well, here's how. A counterexample row, and remember that's what we're looking for to assess equivalence. Those are rows in which statements have different truth values. Okay, so for example, phi is true but psi is false. That's what a counterexample row is, right? It's a row in which there are different truth values, in particular where phi is true and psi is false, or where phi 1 through n are true but psi is false, okay? But notice if the statements are equivalent, then they are all going to have the same truth value on every row. That's what equivalent means. There's no row in which the truth values are different. So if there's no row where the truth values are different, there isn't going to be any row that's a counterexample. So you'll never find a counterexample row, no matter which implication question you ask. And so because there's no counterexample row, the implications are always going to hold. So just to remind you, this is what the one we just did. And these were equivalent. And you'll notice that you're never going to find a counterexample row because they're equivalent. So do 1 and 2 imply 3? Well, we look for a counterexample row. That would have to be a row where we have a true here, and a false there. Okay? But because we know these statements are equivalent, we know we're not going to find a row like that. Okay? And the same thing holds for any other equivalence questions. Do 2 and 3 imply 1? Do 1 and 3 imply 2? No matter which question we ask, we know we're never going to get a counterexample row. Okay, let's go ahead and move on to another example. Here's 3 statements. Here's my joint truth table. Let's ask the questions. I'm just going to number them up on the top for convenience. Are they equivalent? Nope. Row 1, they're different. That's all it takes is one row where they're different. They're not equivalent. Are they consistent? No, there's no row where they're all true. You can just sort of look and you won't find one. So they're not consistent. Okay, let's ask the implication questions. Now, because they're not equivalent, we're actually going to have to look at the truth table to assess the implication question. So we're not going to be able to get out of the work like we could have been able to. We might have been able to get out of the work if it turned out they were all equivalent. We could just then answer the implication questions. Yes, we would just know, but they're not equivalent. So now we have to do that work. Do 1 and 2 jointly imply 3? So again, I'm going to look for the counterexample row where 1 and 2 are true, but 3 is false. And sure enough, row 1, 1 and 2 are true, but 3 is false. So I've got my counterexample row. So the implication does not hold. Okay. Do 1 and 3 jointly imply 2? So now I'm looking for a counterexample row where 1 and 3 are true, but 2 is false. Okay, is there such a row? Sure enough, row 3. 1 and 3, 1 and 3, those are true, but 2 is false. So there is a counterexample row. So the implication does not hold. And finally, I can ask, do 2 and 3 jointly imply 1? So now I'm looking for a counterexample row where 2 and 3 are true, but 1 is false. And sure enough, row 4, there is a counterexample row, so that implication does not hold. Okay, let's do one. I believe this is the last example before we move on to section 2.5. We do 4 statements now. If A, then B, if C, then B, A or C, and finally B. Now, I'm not going to be able to put them in order here. I can get 1, 2, and 3 in order, but 4, because it's B, it's an atomic statement, there's no way it's stuck here in column 2. So that's okay. It just means it's not going to be quite as convenient. But I'm still going to number them just to make my life a little easier. I'll know what I'm looking for. Let's ask our questions. Are they equivalent? No. If you're looking down, you might look at rows 1 and 2. So far, so good. They're all true on both of those rows. But as soon as you get to 3, a difference pops up right there. False, true. Only takes one difference, and they're not equivalent. So no. Are they consistent? Sure enough. Look at row 1. 1, 2, 3, and 4. All those statements are true on row 1. And you can stop looking at that point because it only takes one row to establish that they're consistent. Okay, let's do some implication questions. Do 1 through 3 jointly imply 4? So I'm going to look for any row where all of these are true, but that's false on the same row. Is there any row like that, a counterexample row? Nope, no counterexample row. So there's no counterexample row, so the implication does hold. 1 through 3, or 1, 2, and 3, do jointly imply 4. Do 1, 2, and 4 jointly imply 3? So now I'm going to look for any row where 1, 2, and 4 are all true, but 3 is false. Okay, and bingo, row 6. 1, 2, and 4 are all true, but 3 is false. So there is a counterexample row. So the implication does not hold. 1, 2, and 4 do not jointly imply 3. Okay, let's move on to the last topic. And as you'll see, this is actually going to go pretty quickly. The last topic is validity. And why is it going to be fast? Well, it's fast because we've really done all the work we already need. in order to assess whether a deductive argument is valid, what we do is we just assess whether the premises jointly imply the conclusion. And if they do, then the argument's valid. Okay, and we already know how to do joint implications. There's really no extra work here. So for example, if we look at this argument, and this is just the pizza argument again, this pizza is either pepperoni or cheese. It's not cheese, therefore it's pepperoni. And I try to convince you in chapter 1 just intuitively that this argument is valid. If those premises are true, the conclusion has to be true. But now we can assess it without having to rely on intuition. We can do a truth table, and we can see whether or not the premises jointly imply the conclusion. Well, the premises are here in column 4, that's premise 1, column 3, that's premise 2, and the conclusion is here in column 2. Okay, so I'm gonna ask, do these two statements, the premises, jointly imply this one? So I'm going to look for a counterexample row, okay, where 1 and 2 are true, but 3, the conclusion is false. And you can see there's no row like that. Okay, there's no row where the premises are true, the conclusion is false. So the premises do jointly imply the conclusion, and so that argument's valid. So yes, 1 and 2 do jointly imply 3, and so yes, the argument's valid. Okay. Now you might ask, why does this work? Why is it that we can determine argument validity by joint implication? Okay, well, I'll explain that, and then I'll come back and we'll do a few more examples. Remember the definition of validity from chapter 1, okay? An argument is valid if and only if, by definition. This is a deductive argument. If the premises are all true, the conclusion cannot be false. Or to put it another way, an equivalent way, if the conclusion is false, one or more of the premises must be false. Okay? And that's just what valid means. That was our definition of validity. Well, notice that a counterexample row is exactly a row that defeats that definition. Okay? Meaning if there's a counterexample row, you know the argument's not valid. Why? Okay? Well, remember, a counterexample row is a row where all the premises are true and the conclusion is false, right? If you're assessing whether the premises jointly imply the conclusion, that's what a counterexample row is. Premises are all true, but the conclusion is false. So if you find a counterexample row, what do I mean by saying it defeats the definition? Well, any row where all the premises are true and the conclusion is false means that this part of the definition failed, because if the argument's valid, if the premises were all true, the conclusion couldn't be false. Okay? But if there's a counterexample row, that can happen. You can have all true premises and a false conclusion. So the definition of validity doesn't apply to that argument, so it's invalid. You can also see that it defeats the alternate wording or the equivalent wording, right? Because a counterexample row, being a row where all the premises are all true and the conclusion is false, if the argument's valid, then if the conclusion is false, one or more of the premises must be false. Okay? But again, if there's a counterexample row, that's a row where, yeah, the conclusion is false, but all the premises are also true. Okay? So if there's a counterexample row, this definition isn't satisfied. Okay? So that's why we can use joint validity to, joint implication to determine argument validity. Okay? Let's do a few more examples. Here's an argument. GL, therefore D. And this could be a translation of the following argument. Trees are green, lead is heavy, therefore Elvis is dead. Now, this is like an example I would have used in chapter 1 to sort of, as an example of why, even though the premises are all true and the conclusion is true, the argument is still obviously invalid, right? There's something weird about that argument. specifically the truth, the premises don't have anything to do with the conclusion, right? But we can sort of see this now with truth tables. First, we can do a joint truth table of that argument. And it's going to be a weird truth table because there's no compound statements. It's only atomic statements. And now I'm going to assess argument validity. Do the premises G and L here in columns 2 and 3, do they jointly imply the conclusion D in column 1? Okay. So I'm going to look for a counterexample row, which is be a row where G and L are true, but D is false. And sure enough, row 5, G and L are true, but D is false. So we have a counterexample row. So the implication does not hold, so the argument is invalid. Next example. If D then R, D therefore R. This could be, for example, might be a translation of this. If ducks sink, then ducks are made of small rocks. Ducks do sink, therefore ducks are made of small rocks. Now this is an example of an argument where everything is false, right? Both premises are false and the conclusion is false. But the argument is still intuitively valid. You still think, well, if those premises were true, the conclusion would still have to be true, right? Yeah, they're false, conclusion's false, but if the premises were true, the conclusion would have to be true. Intuitively, you can see that. But we don't have to rely on intuition anymore. We can do a truth table. Here's the joint truth table. And my premises are here in column 3 and column 1. And the conclusion is in column 2. So the counterexample row I'm going to be looking for is one where we have a true and a true here, but a false in the middle. And you can see that there is no row like that. We can't, that pattern doesn't exist. So the implication holds, and so the argument is valid. Okay, let's do one more example. If not A, then K, not K, if and only if not A, not K, therefore J. Here's our joint truth table. And where are our premises in conclusion? Premise 1, premise 2, premise 3. Okay, so the premises are all here at the end, not in order, but that's where all the premises are. And the conclusion is here, J, in column 2. So I'm going to be looking for any row where these are all true, but that's false. Okay, is there any row like that? So any row where these are all true, but that's false. No, there isn't. There's no row like that. Okay, you can look again for yourself if you don't believe me, but there's no row that fits that pattern. So because there's no counterexample row, the premises do jointly imply the conclusion, and so the argument is valid. All right, that is it for this lecture. Study hard.